For statisticians, obviously it would be advantageous to have the smallest confidence interval width or smallest margin of error possible. That way you would be very precise about what your parameter is, right? The smaller interval you have, the more precise your estimate's going to get. Often, though, you shouldn't mess with your confidence level, right? We saw previously that the lower confidence level we have, the smaller interval we have. But if you lower your confidence level, it's going to be more likely that you're going to make a mistake and not adequately represent your parameter. So the only real tool that statisticians have to affect the size of their interval is the sample size, n. And so what we're going to want to do for a lot of problems is figure out, well, okay, if we want our interval to be a certain size, how many people do we need to sample in order to make that happen? Let's check out an example. So here's an example. We're looking at a fitness researcher who's attempting to estimate the proportion of people who exercise at least 4 times a week. And what they want to do is create an approximate 95% confidence interval. And their goal is to see, all right, how many people should they sample to have a confidence interval width of 0.08 or 8%. So here's what we need to think about. Our margin of error equals the stuff we add and subtract from our confidence interval. So I'll write that as Z star, right? The stuff we add and subtract, times p hat times 1 minus p hat over our sample size. So that's what our margin of error equals. And what we're trying to do right now is we are trying to solve for n. How many people do we need to sample? If we were to rework this equation out and solve for n, our equation would come out to be this. P hat times 1 minus p hat over our margin of error divided by Z star, and we'll take that and square it. This is how we can rework this equation to solve what we're interested in, which is n. Right? That's what we're trying to figure out. So what do we know right now? Well, we know we want to create an approximate 95% confidence interval. So, okay. Right? One thing we know is if we want to create a 95% confidence interval, we need to go 2 standard deviations in each direction. So our Z star value is 2. And because we're squaring this quantity, you technically could use the positive or negative version. It's going to end up with the same result. We want to have a confidence interval width of 0.08. And so what that's saying is our interval should span 8%, or proportion of 0.08. And so if we think about it, our sample proportion, p hat, we're going to have to go how much in each direction? Well, we're going to have to go 0.04 bigger than it and 0.04 less than it. So our margin of error that we want is 4%, or 0.04. Our equation asks for the margin of error. So if you're ever given a specific confidence interval width, just divide that by 2 and input that margin of error below. We want a margin of error of 0.04. The only thing that is a mystery to us is p hat. Because p hat is our sample proportion. Well, how do we calculate our sample proportion? Well, we take the number of successes over our sample size. What are we trying to solve for? Our sample size. We don't know this value. We typically have not already conducted a sample to try to figure out how many people we need to sample in the first place. So typically you'll do something like this before you have conducted your sample, conducted your study. We didn't take a sample yet, so how do we know what our sample proportion is? So we're left with an unknown. But watch this. I'm going to take our sample proportion, p hat, and I'm going to just plug in some random values for our numerator. I'll try p hat of 0.1, and then I'll do this quantity out. And if we were to do this out, we end up with 0.09. Let me try a p hat of 0.3. 1 minus 0.3 equals 0.21. I'll try 0.5. 1 minus 0.5 equals 0.25. And I can repeat this process. 0.7, 1 minus 0.7 equals 0.21. 0.9 as p hat, 1 minus 0.9 is 0.09. What we'll notice is the numerator will keep increasing until we get to 0.5. Then it will start decreasing. So we'll notice our numerator reaches its maximum value when we have a p hat of 0.5. Why is that important? Well, what this is going to allow us to do is if we use 0.5 as p hat, regardless of what our sample proportion actually turns out to be, whether it turns out to be 0.1, whether it turns out to be 0.9, if our p hat is 0.5, we are going to guarantee that our margin of error is at most 4% or 0.04. Whatever value of p hat we have, we're going to be able to at least have a margin of error of 0.04. It very well may be lower, but it's never going to be bigger than 0.04. We'll always reach our precision level, and if anything, we'll be more precise. So using 0.5 is this nice safe value for us to guarantee to get our precision rate. So what we'll do is we'll substitute 0.5 as p hat. And if we were to do this out, we end up with 625. What this is saying is if we sample 625 people, our margin of error, which we want to be 0.04, 4%, our margin of error will never be bigger than 0.04. If our p hat turns out to be anything else than 0.5, our margin of error will actually go down. So essentially what we're doing is by using 0.5 is we're taking the worst case scenario into account. If we sample 625 people, we'll never have a bigger margin of error than 4%. It very well may be lower, but it's never going to be bigger. And we always want to at least have our precision rate that we're interested in. What we also need to consider is what if we ended up somehow with a decimal? Like, I don't know, 0.23. So what this would be saying is we need to sample 625.23 people in order to guarantee this margin of error. Well, typically we would round down here. But if we only sampled 625 in this case, there's a chance we didn't sample enough. There's a chance that 0.23 is going to come back to bite us, and our margin of error may actually be bigger than 4% or 0.04. So for whatever decimal we have when trying to find our sample size, what we're always going to do is round up. We're always going to round up whatever decimal we have. So if we do end up with a decimal, in this case, if we did, we should have sampled 626 people.